So by means of quick introduction, my name's Nicholas. I'm a machine learning engineer at Hugging Face. I've been there about a year and a half, and I work on the monetization team, and I interface with a lot of companies, help them with their machine learning projects. I've been working with transformers and mainly NLP, but all sorts of transformers for images, audio, and that sorts for a few years now. Most of what I know is purely self-taught. There's a lot of resources out there. And hopefully what I'm doing today is useful for some people that are learning more about some of the models and use cases that are out there. I'm based out of San Francisco. It'd be cool if people could share where they're calling in from. I think I posted this on LinkedIn and Kaggle, so if you could also share where you heard about this, that would also be useful for me as well. Feel free to drop any bits of info about you personally, what you do, where you work, how long you've been working with transformers or with Hugging Face. That'd be really cool. I really appreciate everyone who has tuned in here today. So thank you once again. In addition to Hugging Face, I also like to spend some of my time on Kaggle, the data science machine learning competition site. So part of this talk will be covering how I used the donut model on a Kaggle competition, basically going over the thought process and the code necessary to get something out of the donut model for this competition. When I first put it out, it was in first place. I'm nowhere near first place now, but it's still cool. I think it has a lot of interesting applications. The overall agenda for this will be first to dive into what the donut model is, what it can be used for, any nuances that are present in it, and then we'll dive more into the competition and seeing how it will be used, and then we'll get into code and seeing how to actually use it. This is meant to be informative and interactive, so if you have any questions, feel free to post in the chat. I'll try and address it as fast as I can. I think there might be a slight delay, so I'll try and stay monitoring the chat and answer your questions as soon as I can. So with all that, let me switch screens so that you can see what I can see. And if everything's working correctly, my face should be in the lower corner and the screen should be showing the repo about Donut, the document transformer. I'll just keep going ahead with that assumption. It looks like in my preview box it is working, so we'll just keep going. So Donut, it has been out for, I think it's put out sometime in late 2022. Donut stands for Document Understanding Transformer. And why this is useful is because you can pass the model an image and then it'll output text based on that image. And so right here, they're showing a few different use cases. Maybe you need to classify an image. Maybe you need to extract information from that image. Maybe you want to answer a question specifically about that image. So this is related to receipts, but you can use invoices, you can use scanned letters, you can use any type of image that has text on it. If you go to Hugging Face and you look at the spaces section and search for Donut to see what other people have been using with it, you can see a lot of different options. Some people are using it for invoices. Someone has something to do with insurance. Cord has to do with receipts. There's all sorts of things here. And I definitely recommend checking out spaces whenever you're getting to know a new model, because chances are someone's already built something and you can see the interesting uses for that model. We'll do a quick little run through of the paper to show the most interesting points, and then we'll dive into more of the details. All right, let me jump back to the top. Okay, so OCR-free document understanding. Why is this useful? The first figure that's most useful is showing what was before Donut. And so there were models like Layout LM that were doing decently on documents, but they often required a step before being passed into the model. And so it would require another model to do OCR. But what Donut allows for is to entirely skip that step. So it's an end-to-end model. You pass it an image, it'll output text. And so they're showing off various aspects that make it advantageous compared to this other approach, such as what was used for Layout LM. Overall, it would save memory, it could save time, and they show that it also can produce highly accurate results as well. If we keep going, we show the same diagram as before with the various tasks. And so the interesting thing about this model is that, yes, it does take an image as input, but the decoder can also be prompted with text to have it do what you want. And so you could train one model to do a variety of tasks. And you could also think of the visual question answering as a form of prompting. So whatever input, text input it might get, it'll then respond to that prompt. But typically, for some other tasks like classification or parsing, your prompt is just a single token that is telling the model, this time I want you to do classification, or this time I want you to do parsing. Let me pause a second, look at the chat. Benedict, hi Benedict, thanks for joining. South Bay, Paula, thanks for joining. Junior data scientist from New Jersey, heard about it from previous coworkers. Carl on LinkedIn, cool. Yes, the live stream will be recorded and available on my channel. Thank you again for attending. Let's keep moving on. One of the interesting things about how they trained this model was they came up with this approach to generate a lot of synthetic documents. And so they called this tool that they used synthdog. And so what this did was generate all these images with fake documents on them. And so a lot of them, the documents are at slight angles. It has noisy backgrounds. This one has like a deck with shoes on it, slightly different colored papers. The authors of this, I believe, are Korean, and so they had synthdog do this in multiple languages, so English, Chinese, Japanese, Korean. And the advantage of this is that you know exactly what text you're putting down on these fake documents. And so the main pre-training task for Donut is to basically do OCR. Like, given an image, it'll transcribe all of the text that it sees. And so if you already know what was put onto this document, then you know what the ground truth should be. And so this is a clever way of generating a ton of data. I believe they did something like 500,000 samples per language. I think they also used some other corpus, some data set of scanned English document images. And then they actually use their own OCR to extract out the language, the text from those images. And so that whole first stage was training the model to read the page, basically. And if you ever have any questions, feel free to post something in the chat. I'll be happy to answer it. Okay, so we have pre-trained down. It was the model's learning how to read, but how do you teach it how to do more specific things like parse a receipt? So it turns out that that's basically the same thing. You're passing the model an image as input, and when you train decoder models, you're actually passing essentially the answer to the model, but due to the way that it's masked, it can't see into the future. So basically, it's if you know how GPT GPT-2, GPT-3 were trained, then this is trained in the same way. I'll get into more details when I cover the code. I think it'll make more sense. But there's not much difference between doing pre-training and doing fine-tuning on a specific task. And so they show a variety of ways that they were able to use the model. They have a form, they have handwriting, they have a receipt, they have, I don't even know what this is, some train ticket, something like that, more receipts, business expense voucher, a lot of different use cases for this. And at Hugging Face, I actually work with multiple companies who are using Donut for a variety of purposes. Some people are within healthcare, some people are within companies working with like customs forms. There's whole sorts of ways that you can use these models. And hopefully today you'll get a better sense of how to use it, and maybe you can even use it for your own company and your own use cases. So let's see, keep going. This is kind of a comparison of what was out there and how Donut does in comparison to them. Compared to a lot of the other models out there, it's beating them. There have been other models since Donut that have been doing better. So notably, Pixdestruct was one of those that has come out after Donut that does better. In my experiments and some other people who used Pixdestruct, it was a little hard to train, but we recently discovered there might have been a bug in the implementation. So Pixdestruct, I'm not going to cover that now, but perhaps at a later point, I'll do another video on that model. Again, just showing various ways that you can use the model. So here's QA pulling out information. And this one on the left is interesting because it's able to read the handwriting and then transcribe that into, I guess, more structured text that would be useful. So it is very powerful in that sense. One other thing I should mention is that the resolution of the images that you pass into the model is important. And so if you look on the right-hand side here, it's showing how this model is doing according to the resolution. So on the left, it's a lowest resolution, 640 by 640. On the right, it's the highest resolution, 2560 by 1920. As you can see, it just basically goes up in performance the higher the accuracy is. And so this model is powerful, and it's a combination of two parts. So there's the image part, there's the text part. And what the authors decided to do was take existing models that can do both of those separately and then combine them together. So they tried a variety of image backbones, so things like ResNet, Vision Transformer, and what they found was Swin generally did the best. And so all of these are actually pre-trained on generic images, not necessarily documents, but all of that knowledge it learned during the pre-training process is actually useful. So that's the image part. For the text part, they took the decoder side of a multilingual BART model that's already been trained on a lot of data. And so they're combining those together, and that gets you pretty far. After attaching them together, then they do the pre-training step to learn how to read from images. I was speaking with the authors of Pixdestruct, and they actually decided to train both of these from scratch, which takes considerably more compute, but they're at Google, they have a ton of compute. And they thought that they never did test what it would be like if they started from a pre-trained checkpoint, but they said it did seem like it was definitely like, well, what would exactly they say? They found that the text model was much smarter than the vision model, that it was hard to train them both together, basically is what they said. And then I guess the notable thing on the left-hand side is the impact of pre-training. So if you just take these pre-trained image and text models and try and fine-tune them on a certain task, so like CORD, which is receipt understanding, they're going to do way worse than if you let it go through that pre-training phase where they're learning how to read. So the synthdog and that other data set of invoices and documents gives it a considerable boost on these tasks. We're nearing the end of the paper of the things that I wanted to discuss. The interesting thing is that the cross attention from the image model to the text model can show you what it's focusing on when it's generating text. And so this is one of the interesting things, is that for the text that it's generating, you can see on the image that the attention was localized to the irrelevant part on the image. So basically showing that it's attending to the right region. Yeah, that's basically all I wanted to cover in the paper itself. So at this point, we'll now jump into the Kaggle competition to see how you could potentially use this. So the competition, it's called Making Graphs Accessible. And the idea behind it is that if you have an image of a figure, whether it's like a line plot, a scatter plot, something like that, can you pull out the data that was used to make that plot? And so let me look at one of the EDA exploratory data analysis notebooks from it to show that, where's an example? Okay, so if you have a plot like this that's showing off a bunch of bar charts, what the goal of the competition is can you extract out that for Malawi, the population is like 800,000 something. For Malaysia, the population is close to 1 million, and so on and so forth, for a variety of different types of charts. So most of them are line charts. Then there's a lot of vertical bar charts, and then there's some scatter and some dot plots, and then a very small amount of horizontal bar charts. And so in a sense, this is just an image to text problem where you're asking the model to look at the image and then generate text based on that image. Donut that wasn't really listed in the paper of things that you could use it for, but it turns out that it works decently. And I think, if anything, it just encourages people to think about a bunch of other options for the donut model. Given any image, you could potentially pull out information from that image. So a lot of different opportunities, and cool that the donut model can do decently on this. And so what we'll switch to now is actually going into the code of how this model works. I see I have a question. Let me address the question first. How does Donut learn the relative position of specific elements in the image to align them and transform information into tabular data? Yeah, so that's part of the incredible part, is that you don't really have to give the model that information. It kind of just figures that out on its own. So how does Donut actually do it? Not entirely clear. But in the process of giving it enough examples, it does start to pick out exactly what it should. And given these categories of line, vertical bar, scatter, dot, I think it does pretty well with vertical bar. I don't think it does that well with scatter plot. So it's not perfect. Like, it's not going to do all of these. So I don't have a great answer for how it actually figures it out. In some ways, it's like the magic of transformers, that somehow these models can actually miraculously understand images, can understand text, can understand audio. And if you make them big enough, people will claim that it's AGI. I'm not going to get into the whole AGI thing, but I think the transformer is pretty remarkable in the sense that it can learn without really much direction into how it should learn. Good question, though. So without further ado, let's jump into a notebook so we can start seeing how to actually use a model like Donut. So what I will do now is actually, let me jump back to the Hugging Face website, because they actually have a lot of documentation on Transformers. So what I would say is whenever you're using something for the first time, come to the Transformers section, go to the documentation, just do a search, and there's usually an explanation, usually the abstract copy and pasted, maybe a helpful image, some tips for how to get going. So this one was put together by the amazing Niels Roga, and he has a nice collection of tutorial notebooks under his repo called Transformers Tutorial. So a whole lot of notebooks for all these different types of Transformers. If you aren't familiar with it, definitely recommend checking it out. And if you're ever trying something new, you might want to check here to see if Niels has built something out before. And so good starting point if you're just getting to know something. More explanation, and there's even a little bit of starter code. And so if you're using one of the pre-trained models, so this time is trained on this data set, in a matter of, I don't know how many lines that is, 30 lines of code or so, you're already being able to classify an image. So in the simplest sense, you need basically two things to load in. One, the processor, and the processor is a combination of an image processor as well as a tokenizer for the text. And you pass the image into the processor as well as, you pass the image into the processor and then you pass the text into the tokenizer of the processor, and you'll pass that both into the model, and the model will output the text from it. So let's jump into it. And what we'll do first is download the data from Kaggle. So if I go to the data section, they have this line down here which shows you how to download the competition data. So jumping back here, hopefully you can see my VS Code. If you can't, post a message. I'll try to make an adjustment. So if I just, I didn't put my key in. In that case, I actually already have this data set. I'll just copy it. Let's see, where did I save it as? I saved it as output, train, test, train, okay. Let's copy the train information. Okay, so in train, we have a lot of annotations. And then I think it's also copying the images as well. And so there's a lot of JPEG files that are there. And then let me copy the test as well. And so test just has a few images. And so I can even, I can load one of these images, and it's pretty small, but you can see that it's a chart of, what is this, total population by broad age group. Okay, so we have the images, we have the annotations, and let's look at the annotations as well to get a sense of what those are like. So they're in JSON format, and I can format it so maybe it's a little bit easier to read. And let me collapse everything or fold all. Okay. So at the highest level, it tells you whether the image was generated or extracted. And so the majority of these images are actually automatically generated by some automated process. It'll tell you what chart type it is. it'll give you the bounding box for the plot. It also gives you the all sorts of text that is on that image. And so let me see. Right, so that first text estimates total population. That looks like it's the title. Right, it tells you it's the title. And it gives you a whole lot more information, more bounding boxes or a polygon around that text. This text isn't actually that important. I won't actually be using it. It gives you more information about the axes. Some of this stuff might be useful if you're training a more complicated model, but in the case of Donut, I took a very straightforward approach, trying to just get a decent baseline. So this data series is the most useful part. And so it's showing you all these X, Y coordinates. So the first one, X, Myanmar, that's here. And it's indicating that on Y it should be, what is that? 4.6 million. So giving you all the XY pairs for this graph. Great. So what we want to do is for each of these images that's provided, we want to match it with the corresponding annotation. And then we need to format the data so that each of these coordinates is valid input for the donut model. And so in that sense, we're going to be training it to generate the XY coordinates. And there's a lot of different ways of doing this generation process. The way that I thought would be best was, let's start with what chart type. We'll first have it predict what type of chart it is. So that's line, scatter, bar chart, dot plot, something like that. And then from there, we'll have it predict all the X values. And so in this case, that might be something like Myanmar. I forget what the next one is, but Namibia, and so on. And then we'll do the Y values afterwards. And so this was, 4.7 million, whatever the next one is, and so on. And so this is, if we train it to output the text in this format, then it'll be very easy to parse and translate back into the format that's best for scoring it afterwards. And so speaking of scoring, I'll cover that as well. And so in this competition, the way that you're evaluated is on basically two ways. So some of these charts are based on numerical data. Some of them have categorical data. And so if it's numerical, you want your model to be as close to the number as possible. So if the answer is, what did I say, 4.7 million, and you say 4.5 million, it's pretty close, but you want it to be, as close as you can. If it's categorical, and let's see, it's so for something like the country name, so like Namibia or something like that, maybe you drop a letter or two, and in that case, you won't get as high as a score as if you get every single letter correctly. So that's basically what the Levenshtein distance is doing. It's a metric of how close two strings are. Another term for Levenshtein is like edit distance. And so how many different characters do you have to change to get from string A to string B? And so a combination of these two different methods, one which is like root mean square error, the other for the numerical data, and then Levenshtein for the text data, will be the ultimate way that the model is evaluated. Okay, so let's first start by matching all the annotations with the images. And I think all these open images is slowing it down. So let me close these and double check the chat to see if anyone has any questions. No questions. Good, we'll keep going. Okie dokie. So first thing I'm going to use is pathlib to make it easy to work with files. So I'm going to use path. Then I'm going to say 1 for the annotations directory, and I guess what is, let's see. So I am in here, so that's train. Okay, so train / annotations. Okay, and then it's images directory. Okay, great. So the nice thing about this is that we can then use the glob function to pull out all of the annotations. So what I'm saying here is look through this directory for all the files that end in JSON. And I did not spell that right. Annotation files. Okay. And this is actually a generator, so let me turn it into a list so I can then look at the first option. So it's just some random file. And if I wanted to, I could, let's see. I'll turn this into a variable. Oh. And when you turn it into a list, you can only do that once. So, okay, first file with open, first file, p. That's just read that file to make sure that it's what we're looking for. Okay, so this looks exactly right. So what we want to do now is come up with a function to go through all of the annotations and store that in a more useful format. So the way that I'll do this is by using the datasets library, and then the datasets library from Hugging Face makes it easy to do multi-processing to make it easy to do fast things like this. So I'm going to import a dataset object, and the dataset object I'll call ds. And what I'm going to do is have all of the let's see. We'll just put all of the annotation file paths in that. And let me delete these. And it's telling me invalid because it is a bunch of path objects. So let me turn them all to strings. Okay, so if I look at this, it says I don't have any rows because external features info don't match. Oh, I also have to change this back into a list as well. Okay, so let me run these two, and at now I have the path to the JSON file. Okay, and so if I check how many there are, I have 60,000 examples. Great, so let's now go through each one of these and pull out the most relevant bits of information. So I'm going to use the JSON library to read each of these files to pull out that information. So again, let me just check what this will look like. Okay, so if it looks exactly the same, but actually now it's a JSON object. So that's super useful. And let me store this as an item, and let me say, okay, this matches exactly what I'm looking for. So now I'm writing a function that will open each of these files, pull out the data that I'm interested in. So again, we're looking for the chart type, we're looking for the X values, and we're looking for the Y values. That's all we need. So the keys that we're interested in are chart type and data series. So we will write a function called parse JSON. And this will be passed as a batch. So batch will actually be a list. So it'll be multiple items. So we're going to have to do it for each one. So let me store this as a list for a file name in, and then what did I call it? Annotation path. So we're opening up each one. Open that file. Oops. JSON.load. So now we have the data from that file. And now what we want to do is chart type, data series, great. So this is pulling out the chart type and the data series from each one, but we actually want to format it in a specific way. So let me double check what this looks like. So it's a list of dictionaries, keys, X, some being Y. Great. So the ultimate way we're formatting this is like a bunch of X values delimited with something. I'll probably use a semicolon rather than a comma, and then a bunch of Y values. Again, I'll probably use a semicolon to make it easy to separate them. So this data series object is going to look like this. So let me do, what's a good way? X, Y equals, so we'll have two lists, one for X, one for Y. So for each row of the data series, we're going to append the corresponding data. And so this data might be a string, it might be an integer, but we're going to convert everything into a string anyway. So what we'll do, we'll say, so what this is doing is going to look in every element of X, map it to a string, and then turn that whole thing back into a list. We'll do the same thing with Y. Look at each one of those, turn it into a string. Okay, so at this point, we have the chart type, we have a list of the X values, we have a list of the Y values. And so what I'll do now is combine all of these so that we actually have like the end ground truth string that we want the model to print out. So that will look like ground truth string equals chart type plus, we'll join all of the X values with a semicolon. We'll do the same for the Y values. But one thing that would be useful here is having something in between these that indicates what's X and what's Y. So I'm going to introduce some special tokens to separate these. And when I introduce special tokens, I'll have to insert that into the vocabulary of the model. And I'll show you how to do that in a little bit. So let's call this xstart. And we'll just do something like this with brackets. And I'll actually put an xend as well, just to make it separated. And I'll do the same with y. Well, let's see. Y, Y, Y. Okay. And then I actually think it makes more sense if the chart type is its own type of token. And so it only has to learn 5 different tokens rather than potentially the tokens that make up each chart type. So to double check all the different chart types that are out there, what I can do, I can take the data set. I already have all of these. So what I can do is I can do something similar to this. Oops. Do this, and then chart type data. Okay. So now that's going through each of the rows of the data set to have a list of chart types. And just to double check what's in there, I can use the counter item to pass in all the chart types. And we can see that we have about 25,000 line, 19,000 vertical bar, 11,000 scatter, 5,000 dot, and 73 horizontal bar. And so let me modify this to be all chart types. And so then we can say we will turn this into the special token. Whoops. We'll put the chart type. Okay, so we're looping through. We just take the set of it, so we're just going to get the unique ones, and for each one of those, we're going to create this chart type token, which basically is just the chart type with angled brackets on the outside. So what we'll do here, let's see, is we'll convert that extracted chart type to the chart type token. So we'll add that here. And then we have to insert the X start and Y start, X end. I'll just type it Y start. Great. Chart token, X start. All the X values, X end, Y start. All the Y values, all the Y end. Okay, so let's make sure that this works. And when we're doing a map function within data sets, we have to return a dictionary. So let's call this ground truth string. And let's see, GT strings equals that. GT strings dot append ground truth string. Okay. Great. So this will parse a file. Okay, great. So one thing I can do before I run it on everything, let me run it on one small thing to see if it works. So parse JSON, it's expecting a list with dictionary, and I'll just use the example that I had. And there's an error. List indices must be integers or slices, not string, for file name in batch. Okay, so I did it the wrong way. So it's first a dictionary, and then it's a list. Okay, so now we have this ground truth string with the chart type. We have the X start, we have a bunch of the X values, we have the X end Y start, and now we have the Y values. Perfect. One thing I would say is that for something like this, there's a lot of decimal values. It's probably not necessary if you're doing root mean square error to include all of these values. It's just more tokens that you have to pass through the model, and it's not going to make much of a difference whether you do 4 decimal points or if you do however many this is, 10 or something like this. I'm just going to leave it for now, but it does seem like something that you could change to potentially make it a little bit easier. All right, so now we have this, so we can pass this into our dataset object to get this ground truth string for every single item. And so if I call, I'll make a second one, and I'll use the map function, and map is just going to look through every single row and apply, or it's going to apply a function to every single item of this data set. And so my function is called parse JSON. I'm doing this in a batched manner, and I'm going to do it in 4 processes. And it worked very quickly. So in 1.2 seconds, I now have all of these ground truth strings for every single item. Great. So now we have the data, and now it's just a matter of figuring out how to pass this into the model. So I'm going to create another function, and this one's going to deal with setting up the model. So the 3 things typically need when you're using a model are the configuration, the processor, and the model itself. And I'm going to pass in a config object so that it's a little bit more flexible. And this is when I need to start using the transformers library. So within transformers, I will need auto processor, vision encoder decoder config, and vision encoder decoder model. Those 3 things are all I need for now. Auto processor is nice because you can just pass in a model name and it'll figure out which processor it needs. You don't need to specify donut processor. And likewise with these, it'll pull out the config without actually having to spell out the actual model. So let's say that config will have a model name. Actually, we can just say this. So we're going to use a pre-trained one. And likewise, we'll have that. And likewise, we'll have this. And then this will be the same for all of them. We're going to pull the pre-trained model for all of these and return them. Great. We got that working just fine. So let's actually pull those. So we have them ready. And one thing I can do at the top is create a configuration class, which will be used to store all of the values. And this will make it easier to organize. So I'm going to jump to Hugging Face to look for which file or which name I should be pulling. So donut base, I'm just going to use the one straight from the people who created it. There is a chance that if you take one of the ones that's already been fine-tuned, so this one on receipts, this one's on question answering, there's a chance that if you take one of these, it might do a little bit better than the one that hasn't been fine-tuned, but I'll just stick with the generic one that's gone through pre-training. Oops, wrong one. All right, here I am. All right, so now we have this. And what I'll do now is say, okay, so now in the future, if I do need to change the model name, I can just change it in the configuration. So here it is, downloading configuration, tokenizer, PyTorch model. It is almost a gigabyte, but it won't take that long to do. Let's see. Still no questions. If anyone does have anything, if anything does seem unclear, feel free to post a question. I'd be happy to answer it. But as a quick summary of what we did, we looked into the annotations to see how we can convert it into the format that we need. We made that ground truth string, which will be used to train the text model, and we loaded in the processor, the configuration, and the model. And this maybe is a small thing, but if I call it git config processor model, I should probably do it in that order. Config processor model. All right, so I have the configuration, I have the processor, and the model. So what's in the configuration? It's just a lot of things about the model itself. A lot of these you don't really need to care about, but we will need to modify some of these so that it can work properly. The processor, it won't really tell you much information, just information about the image processor and then what tokenizer it uses. And finally, the model, if you want to take a look at that. There's the encoder, which is the SWIN model. That's the image part. And then after all of those, there's the MBART, multilingual BART, which is the decoder model. One thing I forgot to mention is that for this model, typical MBART base is 12 layers, and what they have here is 4 layers. And so what they did was remove basically 2/3 of the layers to make it a little bit smaller, a little bit faster. But it probably would make the model better if it had more layers or if it was a little bit bigger. But all of that comes at a cost. It'll run slower, take up more memory, be a little bit harder to train, and it does pretty well as it is. All right, cool. Config processor model. So what we want to do now is make sure that that we add these new tokens. So the X start, X end, Y start, Y end, and all of the chart types. We want to add these into the tokenizer vocabulary. So what we can do is take that tokenizer and call the add tokens function. And what that takes is just a list of all the new tokens that you're adding. So that, if I jump up here, I can copy all of these and add comma. And maybe it's easiest if I do this. Okay. So it said I added 9 tokens. Great. That's perfect. And the other thing that we have to do is, let me double check my notes just a moment. I forgot about the images. Yes, let's add the images as well. And so we can just modify the parse JSON function to also include the images. And so what we want to do, in addition to the ground truth string, we want to include the path to where the images are. And so within, to find the images, the annotations and the images have the same like file name stem. So here it's 0A, 0A, blah, blah, blah. And the corresponding one has the same ID, 0A, 0A. So what we can do is, it's making me, because I opened up 60,000 files. So what we can do is take the stem of the file name. So that's just going to be the ID. We can say image paths. We're going to make a list of that. So file ID equals file name dot, but it's not
I think I need to convert it back into a path object before I can use stem. And then the, what did I say? Image paths, that list. I'm going to add, and I already saved this variable earlier, images directory. Let's convert it back into. So the nice thing about using pathlib is that we can just use this slash operator to join things. File ID dot JPEG. And so, okay, so now it's going to add all of those and images path, image path. Okay, so now that we have that, let's check that it works. And so that seems reasonable. It's giving me the path to the corresponding image. So A934, A934, perfect. So run that dataset function again, and in 1.3 seconds, we have it done for all of them. All right, config processor model. We've added the tokens. Great. So at this point, we will now figure out what to pass to the model. Okay, so the training function itself. So because this is a sequence-to-sequence model within Hugging Face, there's a regular trainer and then there's a sequence-to-sequence trainer. So we'll be using the sequence-to-sequence trainer because it allows for generation for models like this. So exactly what we need. And some other things, let's add the set seed function so we can have somewhat repeatable experiments. Seek to seek. We'll need the training arguments, and then we also need the trainer itself. All right. So in terms of arguments, there's literally like 100 of them that we could set. There's only a few that we really need to care about. So output directory, let's just call it output. I don't really care about the model, so I'm going to overwrite the output directory. And let's see, what else? I don't care about the learning rate, batch size, I won't worry about right now. What else do I need to do? I'll set it to FP16, so mixed precision will train a little bit faster. I'm going to use weights and biases for logging so I can see what's happening. Logging steps, I'll do that every 10 steps. My evaluation strategy will be every epoch. My save strategy, actually I'm not going to save. No save strategy, I'll just save after it finishes training. Well, actually, never mind, I'll save every epoch. Save total limit. So how many do I want to save? I'm only going to save one. Let's see, what else am I missing? Prediction loss, predict with generate true. So what this means is instead of just using like the typical forward pass, we're going to be using the generate function. And so for decoders, when you're generating, you're passing one token in, it's going to predict the next token. It's going to do another forward pass for the next token, and so on and so forth. When it's being trained, you're actually passing everything through the model at once, but there's this causal attention mask so that it can't see any of the tokens that are into the future. If that is confusing, I would recommend looking into Jay Alamar's blog. He has a lot of examples, and most of them are visualized very well. And so if we look up GPT-2, he has one called the Illustrated GPT-2, and it goes all over how decoder models work. So here it's showing it going one token at a time. So when it predicts A, or so given this prompt, it'll then predict A, then it'll predict robot, and so this is why decoders are slow at inference time, but when they're being trained, you're actually passing all of this through at the same time. And so that's somewhat represented here by mask self-attention, but maybe this is a discussion for another time. All right, so we have the arguments. Let's create the trainer. So what does the trainer take? Model. It takes the training arguments, data collator. We have not created the data collator, so I'll comment that out. Tokenizer. Train data set. We have not added that either. Eval data set. So the things that we need to do are create the train data set, create the evaluation data set. Okay, great. So perhaps the simplest way of splitting up the data set is just doing something like this. So there's the train test split function. Okay, so this will make, I'll do it even smaller. 0.1, the test size will be 0.1. Let's shuffle it, and let's do, we could even stratify it by column. And isn't there a seed? And I'll use the seed that I set in my configuration. So let's come up here, and we'll just use the current year. Okay, but we have to add an additional column so that we can stratify by that chart type. Chart types. Okay, so now we have an additional column. Let me, oh, it's not installed. Okay, great. Okay, so we've updated our data set, and now we can split it. Oh, I forgot to update my configuration. Class CFG, come back down. Still complaining. Stratify by column is only supported for class label column, and column chart type is value. Okay, well, we won't use that then. In reality, because the labels are so unbalanced, so where was that? Where you have a ton of line, you have a vertical bar, it would be good if your test set has proportional amounts of each of these. And then another caveat is that because some of these charts are generated and some of them are extracted, what is important to notice is that, where do they say? They say somewhere here that the extracted figures in the training and public sets are drawn from the same set of sources. Figures in the private test are drawn from a distinct set of sources. So most of these are generated plots, but you'll ultimately be evaluated on extracted figures. And extracted figures are a little bit harder to predict than the generated ones. So when you are creating your splits, I'm not going to do that now because it's going to take a little bit more time. What I would do is evaluate on only extracted charts rather than just generated ones. Okay, but keep going on. We'll just do a very basic split. And so if we look at this data set, it's going to create two different splits. One, the train set that has 54,000, one, the test set that has 6,000. Great, so now we have our training set, test set, everything's looking pretty good. Let's set the seed. Okay. Split. So we have train, we have test. Split. Yeah. Okay, so now we have our train data set and our eval data set. Great. So now we just need to work on the collator. And so what the what's going to happen is that when the model's being trained, it needs to read each of these images, create extract the pixel values. It'll do some like normalizing, and then we need to tokenize the text as well. So we can do that at this point here. I promise you, we're almost to the training, so keep bearing with me. We're almost there. Okay. Let's keep going. And I originally planned for this to be an hour and a half, and I see that I'm approaching the hour and a half mark. So what I'm going to do is swap over to another notebook that shows how to do this more conveniently. Just a moment. Some other things that I forgot to add as well. Let's update the configuration with the image height and max length. So image height, let's do 560. Image width, 560. Max length equals 512. Okay, so this max length is the maximum amount of tokens you want the model to generate. This is how you will resize the image. And I would recommend whenever you're using an image model to double check the sizes of your images. And so I did that in this other notebook. And if you can see, most of them fall within like 560 by 560 or so. So definitely whenever you're looking at images, double check. So all the ones that are smaller will get resized to be a little bit larger. All the ones that are a little bit bigger will get downsampled to be fit within that range there. Okay, we have the configuration. Let me run that again. We're coming down to config. We also want to update the processor with some of these. And let's see. Just a moment. So what we need now is the pre-process function. So here we are, pre-process. So what this is going to do when a batch is pulled from the data set, it's going to first tokenize them. And so we need to pass the texts here. And the column I used was ground truth string. So examples, actually like using the word batch better. Ground truth string. So we need the input IDs for those. And then we need to get the pixel values. So what we'll do is this for sample in batch image path. We are going to get the pixel values. And so now we will return, and I need to import a few new things. IDs. And let's see. We don't need that. Okay, so now we're adding pixel values and input IDs, and this is everything the model needs to train. So how does preprocess come into play? So what we'll do, we have to modify the dataset one last time. So we say image dataset equals split dataset cast column from datasets import image. So what this is doing, it's making sure that it's casting this column to make sure it understands it as an image. And we have to tell it that we want you to do this transform whenever data is pulled from the dataset itself. And so that's set. And let's see, max length, padding, true. Let's just set this to max length. That makes it a little bit easier. And now, if everything went according to plan, we can call trainer.train and it will work just fine. But, input IDs, labels. I actually forgot that it needs labels as well. Let me double check. Docs. Seek to seek trainer. Actually, it's not here. I have to go to the almost done, I swear. Go to file, source, modeling, vision encoder, decoder. So what the model is expecting, is there a forward function? From pixel values, decoder, input IDs, labels. And let's see if labels is not none, decoder input IDs is none. Okay, so instead of input IDs, I should set this to labels. And basically what this is doing is telling the model, I want you to generate these IDs from this text. And there's a little shift that needs to be done, but the model will handle that on its own. So that's very convenient. Let me double check everything. And if, it wants me to log in. Wrong one. So now I'm running into an error. Let's see, list index out of range, table, batches, pi arrow. Oh no. Get. Well, this wasn't supposed to happen. And let's see if I can figure this out. Runtime warning, divide by 0 and counted in remainder, fast gather. Why would this happen? List index. Let me make sure my data sets are even working. So if I get an example from this, I get, oh, that's why, because I'm using an image data set. So, right, so now I'm getting pixel values, I'm getting labels. Okay, that's much more what I want. So let me recreate those. And now I get a different error, but it looks like the same error. Let's see. Image df train, annotation path, ground truth, 0. pixel values, labels. Okay. Well, I think we're almost out of time, but we've walked through basically the whole steps of taking the text, the desired output text that you want, turn it into a format that the model can handle, and then loading all the different components of the model itself, the configuration, the processor, the model. And then there's a little mistake that is causing it to not work. I'll have to figure that out, and I can share a notebook on the published video afterwards. I think we're out of time given that we've been going about an hour and a half. So thank you everyone who has joined. And if you do have questions, feel free to leave it in the chat. I'll publish more when the video comes out in a little bit. But thank you everyone. And with that, we will now close this stream. Or let me check for final questions. Oh, it's okay for longer stream. I see. But it may be okay for you, but I actually planned other things after this. I didn't think I would run out of time. So I apologize for having to end it early. Maybe I'll make a video going over the last remaining bit. So I apologize for having to cut it off a little bit early. But thank you everyone for joining. Hope you found it useful and enjoyable. This was the first time I was streaming, so there were a few hiccups at the beginning, but hopefully it'll just get better from here on out. Smoother and more useful, and hopefully just as helpful for anything that you're working on. So thanks everyone. Hope you have a good rest of your day. Hope you have a good weekend, and maybe I'll see you next time.